The modern AI boom was built in the cloud, relying on an environment of essentially limitless computational power, massive server farms, and unconstrained network bandwidth. The physical reality of an automated factory floor offers none of those luxuries. Here, machines operate at high speeds, handling heavy materials under intense mechanical stress. This split-screen table outlines the architectural friction. While the cloud relies on centralized data and infinite compute, the factory floor imposes four strict operational constraints: severe bandwidth limits, microsecond latency budgets, fragmented data distributions, and uncompromising physical safety requirements. Attempting to deploy standard, monolithic large language models or massive deep learning networks in this environment results in system failure. They are too heavy for the local networks and too slow for real-time machinery. To function under these constraints, industrial engineers rely on a highly specialized, multi-layer ecosystem of mathematical models, rather than a single generalized AI. This ecosystem requires a precise architectural build sequence. It starts locally at the physical edge, scales up to dynamic multi-agent control, and finally integrates into an enterprise-wide governance framework. Surviving the industrial environment requires dismantling the concept of an omnipotent AI and replacing it with a localized, rigidly governed algorithmic stack. The foundational layer of this stack is perception. Modern manufacturing relies on constant, high-resolution visual inspection to identify microscopic defects and ensure quality assurance on the assembly line. This diagram illustrates the immediate network problem. High-resolution cameras generate massive, continuous data streams. Piping hundreds of raw video feeds to a central cloud server instantly chokes the local network bandwidth and exceeds the microsecond latency budget required to stop a faulty production run. The structural solution is to move the computation away from the cloud. We place the inference engine directly on the physical edge, right at the sensor. Engineers deploy lightweight machine learning architectures, specifically from the TinyML family, like TinyYOLO variants. These are highly compact convolutional neural networks trained to execute entirely on constrained microcomputers without needing external compute power. This creates a hierarchical manager-worker architecture. Hundreds of tiny edge nodes process their own visual data in milliseconds, passing only a simple binary decision, pass or fail, to a central coordinator, saving massive amounts of bandwidth. Supervised visual classification works when a defect is documented. However, physical machinery often degrades in novel ways, and labeled training data for rare or unseen failure modes simply does not exist. This scatter plot tracks raw sensor telemetry to show how unsupervised learning handles those unknowns. The algorithm does not look for specific defects. Instead, it groups normal operational data into a central cluster. When sensor drift occurs, the new data physically separates from the main mass, immediately triggering an anomaly boundary. By mathematically defining normal operations, teams can execute precise condition-based interventions exactly when a machine deviates from that cluster, eliminating reliance on scheduled manual inspections. The edge layer actively trades the massive computing power of the cloud for ultra-low latency. It allows the factory to perceive its physical reality in real time without suffocating its own digital infrastructure. Moving beyond single spatial images, physical machinery constantly generates sequential sensor streams over time, like the continuous high-frequency vibration logs of a milling machine. This time series chart shows how we map those temporal dependencies. Recurrent neural networks, specifically long short-term memory models, or LSTMs, read these sequential wave patterns to forecast exactly when a tool will fracture, enabling precise predictive maintenance. Forecasting a physical tool break is predictive. Actively adjusting the machine's physical parameters to prevent that break from ever happening requires dynamic control. When a system must constantly trade short-term energy costs against long-term production throughput, static, hard-coded engineering heuristics fail to keep up with the changing variables. As detailed in this sequential logic loop, dynamic optimization requires reinforcement learning. An algorithm like proximal policy optimization, or PPO, executes a physical action, observes the new state of the machine, calculates a mathematical reward based on efficiency, and updates its internal policy to perform better on the next cycle. These PPO algorithms scale horizontally across the facility, They act as the underlying control mechanism for navigating autonomous mobile robots, or AMRs, learning complex obstacle avoidance policies in real time. When managing an entire fleet, multi-agent reinforcement learning decomposes the control logic. The agents actively negotiate physical space among themselves, significantly reducing path overlap and maximizing area coverage in tight warehousing environments. To prevent these agents from learning unsafe behaviors through trial and error, engineers deploy hybrid physics-informed networks. They embed strict laws of physics into the base algorithm, drastically reducing the time and data required to train a safe model. Through sequential modeling and reinforcement paradigms, the AI architecture transitions from a passive observer analyzing data into an active participant dynamically optimizing the physical state of the manufacturing floor. Zooming out from individual machines, modern enterprise manufacturing spans multiple geographic facilities. To train robust algorithms, these separate sites must pool their maintenance insights. The roadblock here is legal and structural. Strict data sovereignty laws, intellectual property protections, and uneven data distributions prevent these facilities from sharing raw historical logs with a central server. Look at the data flow in this architecture diagram. This is federated learning. Instead of moving sensitive data to the cloud, the global algorithm is sent directly to the local facilities. Each site trains the model internally, and only the extracted mathematical weight updates are transmitted to a central aggregator. This hierarchical aggregation overcomes cross-facility bandwidth limits and completely bypasses data privacy laws. The global model learns from the entire fleet's operational history, while the raw proprietary data never leaves its home server. With the machine-to-machine data architecture secured, the final challenge is connecting this massive ecosystem to the human operators on the factory floor. Engineers deploy natural language processing and large language models as knowledge-driven agents to summarize decades of complex maintenance logs and provide operators with instant policy-constraint guidance. To prevent LLM hallucinations, we require strict verification. As mapped here, all raw text generated by the agent must pass through a filtration grid built from strict domain ontologies. Only data that aligns perfectly with verified engineering facts makes it to the operator, ensuring auditable, context-aware recommendations. Enterprise coordination connects global fleet intelligence with rigorous local verification, enforcing tight intellectual property boundaries while fully augmenting human oversight. This diagram maps the complete heterogeneous architectural stack we have built. TinyML processes local spatial data at the edge. LSTMs and PPO execute time series forecasting and dynamic physical control, and federated learning manages enterprise logic across the fleet. But bringing this stack online faces an uncompromising barrier: the physical safety of human workers operating alongside heavy machinery and the intense regulatory scrutiny that comes with it. Because of this, standard black box neural networks cannot be used. An algorithm that delivers highly accurate predictions but cannot explain its internal reasoning is entirely unacceptable for safety-critical industrial decisions. Explainable AI, or XAI, provides the necessary governance wrapper. It mandates that algorithms supply operational teams with human-interpretable attributions, counterfactual scenarios, and precise mathematical verification traces for every decision made on the floor. We enforce layered verification. Continuous reliability checks and validation protocols are executed in the background to ensure the models remain correct even when incoming sensor data shifts unexpectedly. As demonstrated by the bounding box around this robotic arm, hardware relies on certifiable safety envelopes. These geometric borders restrict the machine's physical autonomy. If an AI policy plots a trajectory outside this envelope, the machine mathematically stops, hard overriding the algorithm. Above the XAI layers and the safety envelopes sits the human-in-the-loop adjudication process, acting as the final authority over all automated industrial actions. The most important engineering achievement in smart manufacturing relies on rigid architectural governance. It ensures that artificial intelligence, no matter how advanced, is forced to safely obey the strict laws of physics and facility regulation.